Hi, Algebra 2. This is Unit 4, Lesson 5, and today's a nice, easy lesson. It's called the method of common bases. So we're going to be solving exponential equations, and the way that we're going to do that is we're going to get the bases to be the same. So if we look, there's a rule at the top right here. To solve an exponential equation, we write each side of the equation with a common base. Usually we use 2, 3, or 5. And then once the bases are the same, you can set the exponents equal to one another, and then you just solve that equation that you're going to write. So if we're looking here in exercise 1, notice the bases are the same. So all I do is I take the exponents and I set them equal to each other. So again, these are the bases. The bases need to be the same, and once the bases are the same, then all I do is take those exponents and set them equal to each other. Done. That's it. Now question B has an e to the 2x and e to the 16th. E is actually, we're going to see it when we do logarithms in the second part of the chapter. So e is an irrational number. It's equal to 2.71828, ... It keeps on going on and on, sort of like pi. Okay, it's named after the person who discovered it, Euler. So again, the bases are the same. So as long as my bases are the same, I'm just going to take those exponents and set them equal to each other. And then I solve for x. So I divide by 2, x equals 8. Done. Now the next one, C, I have 10 to the 2x equals 100. I don't have the bases the same, but I can easily write 100 as 10 squared. Now that the bases are the same, I can take those exponents and set them equal to each other and solve for x. So that's basically what I'm going to be doing on the next exercise. I have to get those bases to be the same, so I need a common base. That's why this is called the method of common bases. I get a common base, and then once the bases are the same, I can set the exponents equal to each other. So exercise 2a, I have 2 to the x equals 16. So the 2 is fine. The problem is the 16. I have to write 16 as a base of 2. So 2 to the what power equals 16? 2 to the 4th power equals 16. Now that my bases are the same, I set my exponents equal to each other. Done. Next one, I have 3 to the x, which is perfect, but I'm going to make 27. I'm going to write it as 3 to what power is 27? 3 to the 3rd power is 27. My bases are the same, so all I have to do is set the exponents equal to each other. Next one, I have 5 to the x equals 1 over 25. So I'm going to, this 25 is actually 5 to the x equals 1 over 5 squared. Okay, but I need to bring that up to the numerator. So it's really 5 to the x equals 5 to the negative 2. And now that my bases are exactly the same, both in the numerator, I just take those exponents and set them equal to each other. A little bit trickier. And D is even a little bit trickier. So I'm going to write 4 as an exponent of 2. That's 2 squared. I'm going to write 16 as an exponent of 2. So it's 2 to the 4th power is 16. But I also have that x that's hanging out. But remember, a power to a power, you're just multiplying those. So that's really just 4x equals 2. I'm taking those exponents and I'm setting them equal to each other. So x equals 1/2. All right, remember, when you have a power to a power, you are multiplying those exponents. So that's why right here on that 4 to the x, I'm multiplying them and I just got 4x. So that was a little reminder, and we're just going to practice that down here because that's what we're going to be doing more involved equations on the next page, and make sure everybody's comfortable with this. So a power to a power, and the way you're going to remember it is I have parentheses between these numbers. There's a parenthesis between the 3 and the x, so that's just 2 to the 3x. Next one, 3 squared to the 4x. You're just multiplying the 2 times 4x is 3 to the 8x. A power to a power, you multiply those exponents. Negative 1 times 3x minus 7 is 5 to the negative 3x plus 7. That whole thing is in the exponent. And then 4 to the negative 3 times 1 minus x squared. This negative 3 is going to be multiplied by the whole thing. So it's 4 to the negative 3 plus 3x squared. And that's my answer. All right, let's see what I have on the next page. I think I'm just solving some more of these. And I have a multiple choice to try because those are always on a test or a Regents. Solve each of the following equations by finding a common base for each side. Again, common bases are usually 2, 3, or 5. So I want to write 8 as a base of 2. 2 to the third power is 8, but I still have that x. And I want to write 32 as a base of 2. 32 is 2 to the fifth power. So you really need to know these exponents. You can always use your calculator if you need to. Now that I have a common base, I just take those exponents, set them equal to each other, and I'm going to get a fraction. No big deal. X equals 5/3. 9, I write it as a common base of 3 squared. But again, that whole thing is to the 2x plus 1. And 27, I'm writing it as a common base of 3. 3 to what power is 27? 3 to the third power. And then I need to multiply these. Power to a power I'm multiplying. So that is 4x plus 2, because that 2 is going to be multiplied by that whole thing, equals, and on the right side I just have 3. So I subtract 2, and x is just 1/4. This one over here looks a little tricky. Remember, we're usually using common bases of 2, 3, and 5. So I have 25 and 125. Obviously, I'm going to use 5. So 125 is 5 to the third. Don't lose that x. All right, and then I got like a mess over here. 1 over 25 is really 5 to the negative 2. Right? 1 over 25. 1 over 25 is 1 over 5 squared. But I don't want anything in the denominator. I need to bring that back up, so it's just 5 to the negative 2. But don't forget, don't lose that 4 minus x. So I need to multiply. 3 times x is 3x, now that I have common bases. On this side, negative 2 times 4 is negative 8. Negative 2 times negative x is positive 2x. I'll subtract 2x, and I get x equals negative 8. So definitely getting a little trickier. We're going to practice these again tomorrow. Make sure you're comfortable with them. But you're basically getting a common base. Most bases we use are 2, 3, or 5. And once you have a common base, then you can just set those exponents equal to each other. All right, so 2, I already have a common base of 2. Great. 64, I need 64 to have a common base of 2. 2 times what? To what exponent is 64? If you don't know, check it out in your calculator, but it is 2 to the 6th power. Now set these exponents equal to each other. So I'm going to add 3. And x equals the square root of 9. Okay, but there are 2 answers when I do that. It's positive 3 and negative 3. 3 times 3 is 9, and negative 3 times negative 3 is 9. So there are 2 answers. Choice 1. And I have one more multiple choice here. At what x coordinate will the graph of y equals 25x minus a intersect the graph of y equals 1 over 25 to the 3x plus 1? So basically, I'm going to set these equal to each other. They both equal y. I want to see where they intersect, so I'm going to take them and set them equal to each other. This is just a mess. I got x's, I got a's. All right. And what does this say? 3x plus 1. Let's find a common base. 25 is just going to be 5 squared. Don't lose your x minus a. That's still hanging out up top. 1 over 125 is 5 to the negative third. Again, that whole thing is to the 3x plus 1. You've got a power to a power. So on the left, I have 2x minus 2a. That 2 is multiplied by everything. And on the right, I have negative 9x minus 3. I'm just going to simplify it as much as I can, try and get x by itself. But notice my answers all have a's in them. The a's are not going anywhere. The a's are going to be part of your answer right there. So I'm going to add 9x, combine my x's, and I get 11x minus 2a equals negative 3. I am trying to solve for a. So I'm trying to solve for x. So I'm going to bring this 2a over to the right. So I have 11x equals 2a minus 3. And then to solve for x, I'm going to divide by 11. So x is 2a minus